So lesson 15.4, graphing exponential functions. So I'm going to do this one a little differently than the other lessons. Instead, what I've decided to do is use the teacher edition, which already has the answers filled in, and kind of explain these, because I think a lot of this is just going to tie back to the previous 3 lessons for 15. So one of the first things we wanted to do is match the graph with whatever function is noted here. Now, you can obviously do this on your calculator, but instead what I would like to do is talk about the actual function itself. So one of the things we focused on is if b is a value less than 1, then the function must be decreasing. And if the value is greater than 1, then it must be increasing. So if we look at our examples here, the only one where b is less than 1 is this one. So we need to find a value or a function that is decreasing, which was b. That's the only one that is going down. Now, technically, d is also going down. It's decreasing, but we learned in transformations that when you flip a function over the x-axis, you do that by multiplying by negative. Therefore, the value of this function must always be a negative, which is why it is d. So then all we have to do is we have to choose between graph A and graph C here. And the difference in these is our A value. A here is 3, A here is 0.5. Otherwise, the functions are exactly the same. So what that means is, since this is 3, this one will be growing at a faster rate than this one is. So if you look at the 2 graphs, this one goes up quicker than this one does. This one goes up, but it's not as fast. Our x's have to increase more in order for our y's to increase. So therefore, C corresponds to equation 2, which is multiplied by 0.5, and A corresponds to equation 1, which is multiplied by 3. Next, we want to focus on question D. The other previous questions basically take place in the explanation that we just did. We'll talk about domain and range a little bit more as we do these other problems, but what is the y-intercept? The y-intercept occurs when x is 0. So if you put 0 in here, we said anything to the 0 power is 1. So this is 1. So our y-intercept ends up being our a value for our general form of the equation, so 0.5. So we're going to use this example to help in identifying domain and range, but also talking about some end behavior notation. So I'll come back to that in just a second. The easiest way to determine domain and range is always to look at a graph. So in this case, our domain is our x values. Well, the function continuously goes to the left and will always keep going to the right. Therefore, our domain for this particular function is all reals. It is a continuous function. It's connected. Our range are our y values, which means this goes from, and it will never make it to 0. It gets very, very, very close to 0. It gets really close to the x-axis here, but never gets to 0. We just get really, really, really small decimal values. So our range is from 0, not included, so y is greater than 0 because it goes up. Now, let's talk about end behavior. End behavior is what the function is doing on the left end and the right end. On the left end, this is as the function approaches negative infinity. That is this notation right here. X approaches negative infinity. So what is this function doing as we keep going further and further left? Well, it keeps getting closer and closer to the x-axis, which means the value of the function is 0. It's approaching 0. Again, it never gets to 0. We talked about how it gets really, really, really small decimals, but it never gets to 0. So as x approaches negative infinity, the value of the function is approaching 0. Now that brings us to an important point. Whenever we talk about the value of a function, we're talking about the y value, Now, as far as the end behavior on the right, as x approaches positive infinity, as we move along the function on the right, this keeps going up and up and up. So as x approaches positive infinity, the value of the function is approaching positive infinity. It is going up forever. So we need to be able to read in behavior, looking at notation here, as x approaches positive infinity, the y is approaching positive infinity. As x approaches negative infinity, y is approaching 0. Now, why do we say the word approach? Again, it never makes it to 0, gets very close. It approaches infinity. Infinity is infinity. It is not a set value, so it never ever makes it there. So here's an example of a function. A is 3, b is 4. We know since b is greater than 1, it is going to increase, and since a is a positive, it's going up. So we can put this in y equals, just put our function in, go to our table, start at -1, go by ones, and we can get the values here. Very, very easy. We identified a and b here by looking at the function itself. Again, the y-intercept is the value of a, because we get the y-intercept when we plug 0 in for x. If we plug 0 in here, anything to the 0 power is 1. Therefore, it is a value of 3. Now, as we do in behavior, as x approaches infinity, again, what you want to do is take these points, graph them, and make a smooth curve connecting them. So as x approaches infinity, so as x goes to the positive right direction, the function keeps going up. So y is approaching positive infinity. As x approaches negative infinity, going to the left, again, the function is approaching 0. It won't reach it, but it gets, again, very, very small decimal values. So at this point, what I would like you to do is take the given function on your turn, f of x equals 2 to the x power. Go ahead and put that in y equals. You can go ahead and graph it on your calculator. What you may choose to do is use a similar scale as the graph up here. So go to Window, do x from, each of these is going by 1, -5 to +5. Go by ones. Your y's go from here, -30 up to +60, and you're going by 7.5. So your scale here is 7.5 each time. Then you can graph the function and look at it, and as you look at it, pay attention to your a and b values, know what your y-intercept is, and then look at the in behavior as you're looking at the graph on your calculator and see if you can answer these questions. I'll give you a few seconds here to do so, and then I'll reveal the answer. Okay, so here you go. Here's a table of values to get points. Okay, they've used 4 points. Personally, I would recommend that you do at least 5, but 4 is okay here. So you get a pattern, you connect it. So again, you can look at your A, B values. You know your y-intercept is the value of A. Your in behavior as x goes to negative infinity, it's approaching 0. As x goes to positive infinity, again, the graph is going up towards positive infinity. Now, don't assume every problem has the same in behavior. It is all dependent upon what your values of A and B are that determine your in behavior. So it's always a good idea to graph them. So I've skipped example A since it's completely worked out for you. So here's a prime example where we talked about where A and B are different. Here A is a negative. Again, when you multiply by negative, we talked about how it flips or reflects over the x-axis. So now this graph is going down into the negatives. That's going to change our in behavior. Again, you can go to the table to find points. Connect your points with a smooth curve to get your graph. Pay attention to the scale here if you want to graph this on your calculator. Set your window up to match the given window. A is -3, B is 4. Again, your A is your y-intercept. In behavior now, as x approaches infinity, as you go to the right, this is now going to negative infinity. Why is that? Because we multiplied by a negative, or A was a negative value. Again, as we go to negative infinity, our graph is approaching 0. It's just approaching it from the negative side rather than before being on the positive side. So again, here's a your turn problem. Given the exponential function here, identify your a, b, y-intercept, and end behavior. So go ahead and take a minute to do that on your calculator again. I'll give you a few seconds here, and then we'll check this answer. Okay, so again, we generated a table of values, plotted those. Because it was multiplied by negative, our function is going down. It's in the negative range. And you can look at the answers here. So hopefully by now we're starting to get an understanding of this end behavior. It's just a notation, so make sure you understand the notation. Again, there are different ways to do notation, and I'll address some of those later on, but for right now we're going to stay with this particular notation. So again, I skipped example A and explained 3 because it's completely worked out for you. And now I want to look at this example. Here our A is positive, so I know this one's going up as far as a direction. However, in the positive range, I should say. But because my B is a value less than 1, this will be a decreasing function. So again, they've generated a value of points here to get ordered pairs. So I am in the positive quadrants for my values. However, this function is decreasing because my B was a value less than 1. You identify your A and B. Again, your y-intercept is the value of your A. So now as we look at the end behavior, as x approaches infinity, so as x goes to the right, the function itself is approaching 0. So this is different than before because, again, we have a b that is less than 1. When our b was greater than 1, our function was going this way. So now it's kind of reflected over the y-axis a little bit. As x approaches negative infinity, so as we move towards negative infinity along our function, our y is now going towards positive infinity. So again, dependent upon the values of a and b are going to determine how your exponential function is graphed and what the end behavior looks like. So again, we have a your turn problem with a given function. I want to give you a few seconds once again to put this in the calculator, look at the graph itself, and determine the end behavior, and then we'll check this. So very similar to the example that we just did, because this is less than 1, this is still positive, so it's on the positive quadrants in our terms of our y value, but it is a decreasing function because b is less than 1. So here's our end behavior again. As x goes to infinity, this is approaching 0. As x goes to negative infinity, the value of the function is going up towards infinity. So as before with the explain 4, I've skipped example A because it's worked out. We're going to look at example B. So now we have a scenario where A is negative and B is a value less than 1. So because B is less than 1 here, sorry, get the right arrow here. Because b is less than 1, typically our function decreases. But because it's multiplied by negative and is flipped over the x-axis, it has now become an increasing function. So it has changed the behavior overall. Again, we can do points here, plot those points, connect them, look at your a and b. But now our end behavior, as x approaches positive infinity as we go to the right, the value of the function is approaching 0. We're getting closer and closer to the x-axis. As x approaches negative infinity, so as we go to the left on the function is going down. So now y is approaching negative infinity because it's going down. So here again is another your turn with the given function. And again, I'm going to give you a few seconds to do this on your calculator. So as before, here's our answer. You can do a table of values here. You get your A and B. Again, your y-intercept is the value of A. Now our end behavior, because again it was multiplied by negative and our B was less than 1, B is less than 1 typically means it decreases, but because it's flipped over the x-axis with this negative, it now becomes an increasing function. It just always stays in the negative quadrants. So we've kind of skipped over the elaborate questions, but I think this is a good one. It says y is 3 times negative 0.5 to the x, not an exponential. And because our b here is a negative, and you can go back and look at the general form for an exponential, and it talks about b being a positive value, but the reason is because when it's negative, it alternates between positive and negative. So if x is 1, this is a negative value. If x is 2, you square this, anything squared now becomes a positive. So because it alternates from positive, negative, negative, positive, back and forth, it's not a continuous function. It jumps around, so it is no longer an exponential function. So I think that's an important concept just to understand. It's also why when we give stipulations on functions, that's the case, because it can't just always be a positive or negative. It depends on the type of function itself. Okay, so you will be doing numbers 1 through 19 odd for this homework, but the reason I brought this page up is because I did want to point out you are stating A and B and the y-intercept for each of these functions. However, you're doing all your graphing on the graphing calculator. Okay, you're not having to draw a graph for any of these problems. Now, if it generates a graph for you and asks you to put it on the graph, you do so, but for these particular problems, you're just looking on the calculator. So again, you're doing problems number 1 through 19 odd.